All right, guys, we're going to get started in a minute. I just need to grab my charger. Done. And I'm brewing a cup of coffee. Now I'll go grab that and we'll get started. But we have a lot of things to talk about today. I was going to try to run through the notes. It would have been really nice and easy if we'd had like the smartboard presentation files, but we don't, so that's okay. So I'm going to make things quick and to the point. Here are the basic ideas that we're going to talk about. We have to finish 2.1. The last thing that we need to talk about is what is a transpose of a matrix, and then some of the properties. Lesson 2.2 introduces the inverse of a matrix, and then we'll look at what the inverse of a matrix of a 2x2 is. And then in general, how can we determine the inverse of a matrix that's larger than 2x2? Because you probably know the formula for determining a 2x2 matrix inverse that's using the determinant. But with something larger than a 2x2, it's slightly different. And we have a little bit of easier methodology since we know a little bit about the identity matrix. Lesson 2.3, we're going to look at the characteristics of the inverse. That's going to be really quick because I'm really just going to point you to page 129 is a list of like A through L properties of the inverse matrix. And we'll look at a few of those. And then we'll look at the inverse transformation. So we know that matrices and matrix multiplication can be thought of as a transformation or some sort of function. Well, the fact that there are inverse matrices would imply that there are also inverse functions. Okay, so a way to get from your codomain back to the domain. In lesson 2.4, we're going to talk about partitioned matrices, and we want to talk about also inverse partitioned matrices, but we might not get that far. I might just cut it short and then we'll finish lesson 2.4 and then start 2.5 on Wednesday. All right, let me go grab my coffee. I'll be right back. It's not biting down so hard. So I like this. No. Okay. All right. Okay, let's get started. Let's say we have matrix A, B, C, D. Matrix B is 1, 2, 3, 4, 5, 6, 7, 8. Matrix C is, I don't know, 1, 1, 1, 1, 0, 1, 0, 1. The transpose of a matrix, denoted as AT, takes your row 1 and makes it column 1. Sneeze. No, I don't. Oh, I wrote in the circle. You gotta remind me I can't write here. Okay, I can't write there. So transpose of a matrix takes the row, makes it a column. Takes the row, makes it a column. Right, same thing here. Takes this row, made it a column, takes this row, made it a column. So since you couldn't see the original C, let's say here's transpose of C, what would be the regular C? Well, I take the column and make it a row. Take the column and make it a row. Column, row, column, row. So that's what the original C said up there. Okay, and that's really it for 2.1. Now, there are some interesting properties of transposed matrices, like the, let's see. Obviously, the transpose of the transpose is the original matrix. Assuming A and B can be added, the transpose of the sum of matrices is the sum of the transposes. It works with scalar multiplication as well. That's not too interesting, but what is interesting is the multiplication. So the product of AB transpose is the product of the transposes in reverse order. And that would make sense, right? Because when we multiply matrices, it has to do with whether or not I can multiply them, has to do with the row and column orientations. So if I want the transpose of the multiplication of two matrices, it's analogous to multiply the transpose of each matrix, but in reverse order, because I'm changing up the column and row orientation. Okay. But I'm keeping terms in the same sort of place. Okay, so that's it for 2.1. Nice and quick and easy. We're going to move on to 2.2 now. And 2.2 is going to take up most of today. 2.3 is going to be pretty quick. And then 2.4, we'll see what time it is. I'm going to erase my circle. All right. So, inverse of a matrix. We know that, let's see, 2.2 inverse. We know that the number 7 has an inverse, 1 over 7. And when I multiply those two together, I get the identity. That's the definition of an inverse. The definition of an inverse being through multiplication by the inverse, I should get the identity. In other words, given some inverse or given some number A, the inverse of A should give me the identity. The same thing is true for matrices. Given some matrix A, multiplying by the inverse should give me the identity. Now, if A is an n by n matrix, I get the identity matrix that has the dimensions n. So that's going to be our goal, right? Now, knowing that, we should be able to take this matrix and obtain the inverse by solving this equation, right? Right? So I could set up a system of equations, right? Negative 3a plus negative 4c has to equal 1. See, negative 3b minus 4d has to equal 0. Okay. Then let's see, a plus c has to be 0. And b plus d has to equal 1. Okay. All right, and I could go through here and solve these. Well, this, first of all, implies that A and C are opposites. And this here implies that B is D more than 1. Oops. D less than 1. Okay. So we'll use those ideas up here so that we can get a system of two equations with two variables that we could solve. A is negative C, minus 4C. Okay. And B is 1 minus D. Or D. All right. So from here, we should be able to get that C is negative 1, A is 1. And from this, we'll get that B is 4, which means that D is 3. So A inverse is 1, 4, negative 1, 3. Okay, great. So the property of inverse allows us to come up with a formula or a methodology for determining the inverse, but we should know, smarty pants who already know all of this from pre-calc, know that there is actually a way to determine the inverse matrix using what's known as the determinant. All right. So here's the long way. Now let's look at the short way. Oh, green. Green does not erase well. We won't be using green. Man. Screen does not want to come off. Let's try blue. Okay. There. If matrix A is a 2 by 2 matrix, then the inverse of matrix A is equal to 1 over AD minus BC times right? Yeah. Okay. So if matrix A is a 2 by 2 matrix, right? A, B, C, D, then I can get the inverse of a matrix by using the determinant. Determinant ant. Okay. Okay. So let's try that with this and see if we get the same thing. So the determinant of A, 1 over, let's see, A, B, excuse me. Oh, whoops, I got those mixed up. It's AD times BC. So AD minus BC, that's -1. Okay. So we have -1 times flip A and D, and then invert. Ooh, that's 1, not -1. Excuse me. We have a 4, and we have a -1. And if I multiply by 1, I get what I had gotten there. So the inverse of a 2 by 2 matrix, use the determinant. Okay, so what good is a inverse matrix? Well, just like with basic algebra, we can use the inverse of a matrix. Let's see. Given the matrix equation AX equals B, if A were this matrix, I could multiply by the inverse This would give me the identity matrix, which multiplied by anything is itself. So now I have a good way of determining or solving for x using the inverse matrix, right? And this is typically how you solve matrices with your graphing calculator, right? At least in Algebra 2, this is the way we did it. If you needed to solve this sort of equation, you typed in A, you got the inverse of A, you multiply the inverse of A by B, and you got your solution. So that will be the ultimate goal of the inverse matrix, or the ultimate purpose of the inverse matrix. Oof, this green really sucks. We're going to sweat erasing. All right. Okay. Let's see. All right. So let's do an example. We want to solve 8x1 plus 2x2 equals 2. Let's make that a 6. And 5x1 plus 4x2 equals -1. Okay. So it's okay to say that the inverse of this matrix times our solution matrix should give me x1 and x2. We just need to figure out what the inverse of this first matrix is. Okay, well, the determinant is 1 over A times D. It's 32 minus 30 is 1/2. All right, so we have 1/2 times flip A and D and negate these guys. I get 2, -3, -5/2, 4. All right, so 2, -3, -5/2, 4 times 2, 1 equals 7, -9. We take a few shortcuts today for time purpose. All right, which is x1 and x2. All right. So the main purpose of inverse matrices is to solve systems like this by hand. So in other words, to solve systems like this on a quiz or something where you aren't allowed a calculator or something. So I would definitely bet that solving a system of probably more than 2 equations and 2 variables using the inverse matrix is going to be on the quiz. So let's look at how could we determine the inverse of a matrix of something larger than a 2x2 matrix. I guess I should hit on some vocabulary. If matrix A is invertible, in other words, if there is an inverse for A, then that matrix is called singular, I believe. Let me double check. No, if it is not invertible, it is singular. If it is invertible, it is called non-singular, or just invertible. But another word for a non-invertible matrix is singular. And if you think about the equation for finding the inverse of a matrix, then a matrix is not invertible if matrix A is singular if and only if AD minus BC is 0. Right? In other words, if I have to end up dividing by 0 in my determinant, if my determinant is 0, then I'm dividing by 0 and can't do that. Well, we can't do that. All right. Yeah. Now, Theorem 6 from your textbook talks about a few properties of the inverse. In other words, like the inverse of the inverse is the original matrix. Let's see, the inverse of A times B is the inverse of B times the inverse of A. So sort of the same idea with our transpose matrices. And let's see, the inverse of a transpose is the transpose of an inverse. So given matrix A, if I were to take its inverse or find its inverse and then do the transpose of that, it would be equivalent to first take the transpose and then find the inverse. Okay. So you could always look those properties up. Okay. So now we need to talk about elementary matrices. I'm going to double check my email to see if anybody's trying to talk to me. Also, I don't have the question and answer thing pulled up. Okay. No, that's good. Okay. All right. How long have we been going? Okay. All right. Elementary matrices. So an elementary matrix is any matrix an elementary matrix is one that is obtained by performing a single elementary row operation on an identity matrix. Okay. Oh my God. Okay. Elementary matrix examples. Right? Flip R1 and R3. That's just one elementary row operation, and then I get the identity matrix. Okay, how about 1 0 0 2 1 0 1? Oops. So 0, 1. I just have to do negative 2 R1 plus R2 to obtain a new R2, and I get the identity matrix. Right. 1/7 R2 to get a new R2. One elementary row operation yields the identity matrix. These are all elementary matrices. All right. What's good about elementary matrices? Well, elementary matrices are always invertible because row operations are always reversible. In other words, I could take the elementary matrix, or I could take the identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1, and I could have done this backwards. I could have taken R2 and multiplied by 7 to get a new R2 to get back to this, right? All of these elementary row operations can be done in reverse order to get back what you started with. So all elementary matrices are invertible. So given some matrix, elementary matrix E, let's take this to be E. The elementary row operation negative 2 R1 plus R2 to obtain new R2, if I were to do that in reverse order to the identity matrix, I would obtain the inverse of E. Okay, so let's take my identity matrix 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. And if I were to do this in reverse order, in other words, take 1/2 of R2 and add to R1 to obtain a new R1, right? Should be the inverse matrix of this matrix. Okay. If an elementary row operation is performed on a matrix, an m by m matrix A, the resulting matrix can be written as EA, where m by m matrix E is created by performing these same row operations on IN. For example, fortunately, this is one of those sections that has a ton of just written stuff on the slide, so I'm trying to filter through to see what I can actually say. And then find some examples. So this is example 5 from the notes. I believe the notes are on Blackboard from last year from Anton's class. Okay, so find the inverses of the previously given elementary matrices. Let's see, find the inverses of the okay, and the elementary matrices that we're referring to are the ones that we just looked at. 0, 0, 1, 0, 1, 0, 1, 0, 0. We already did this one, but we'll double check and make sure that I did it right. And then what was it 1, 0, 0, 0, 7, 1, 0, oops, 0, 1. All right. So here I flipped R1 and R3, right? So to get the inverse, I'm going to flip R3 and R1 of the identity matrix. So it is its own inverse, right? Which is pretty nice. Okay. So in this case, it was its own inverse. Let's see. I don't think we did this one correctly. So what we had to do here to get the identity matrix was multiply -2 R1 plus R2 to get new R2. All right. So let's see. The opposite of that would be multiply R1 by 2 and add to R2 to get R2. Okay, so I guess I did do that one wrong. So the inverse of this matrix would really be oh, excuse me. I see. I'm trying to find what it takes to get from the identity matrix to the original matrix, and then I'm doing the opposite of that. So to get from the identity matrix to this matrix, I would multiply R1 by 2 and add to R2 to get a new R2. That would give me this from the identity matrix. So the opposite of that would be to multiply R1 by -R2 or -2 and add to R2. So that's how I would get the identity here. Okay. So then that makes more sense for this one, because to get from the identity matrix to this, I would be multiplying row 2 by 7 to get a new row 2. So the opposite of that would be divide by 7. So my identity matrix is 1 0 0 0 1 7 0 0 0 1. Okay. Not the identity, excuse me. That's my, let's call this C, this B, and this A. This is inverse A, inverse B, inverse C. Yes. And then, of course, you can check the work for these. If you multiply inverse C by C, you should get the identity matrix I sub 3. All right, so I like the example in the textbook better than the example in the notes for this. So we have now an algorithm for finding the inverse of A. Okay. Row reduce Okay, so row reduce the augmented matrix AI if A is row equivalent Okay, so this is going to be the algorithm that we use. So we're going to look at the augmented matrix A with the identity matrix of the equivalent size, and we're going to row reduce that. In other words, we're going to make A look like the inverse, or excuse me, we're going to make A look like the identity, and what ends up here will be my inverse. Okay. If I can't do that, then that means that A is singular, or in other words, A does not have an inverse. It's not invertible. So I need to clean this. It's pretty grimy. All right. Let's look at an example here. And we'll go back and look at the first example from the notes. Is that one? Okay, and we want to find the inverse of A. So the augmented matrix AI looks like this. Right, there's the augmentation happening right there. Okay, so my goal here is going to be to row reduce this augmented matrix. So in other words, this has got to be a 0. I want these to be 1s, and it would be not. It have to be able to get a 0 over this one. So anyway, I want this to look like the identity, or excuse me, to look like the identity. All right. So the first thing we can do is add the two rows together. So we'll do row 1 plus row 2 to get a new row 2. It's going to give me 1, 4, 1, 0, 0, 7, 1, 1. Right? All right. And then oh, excuse me. Is that supposed to be a -3? That wasn't supposed to be a -3. I was going to say that's going to not work out. All right. So 4 plus -3 gives me 1. Much better. Okay. Coming back this way, we'll now do -4 row 2 plus row 1 to get row 1. Right? So we get 1, 0, -4. Oh, whoops. Let's see, -4 row 2, it's -4 plus 1 is -3, -4, 0, 1, 1, 1. So here's I, and here is the inverse of A. All right, very cool. Okay, so there's my algorithm for finding the inverse of A. Now, obviously, we did that with a 2x2 matrix, but it could be done with a 3x3 matrix or something higher. So let's look at an example of that. Right, that was the point of finding this algorithm, was not every matrix is 2x2, and we still need to be able to find inverses. So let's see. Let's let A be 2, 0, 0, -3, 0, 1, 0, 1, 0. Okay. And we want to find its inverse using that algorithm. So 2, 0, 0, negative 3, 0, 1, 0, 1, 0. 0, 0, 0, 0, 0, 0. All right. All right, so let's see. I guess the quickest thing to do would be we could switch these two rows. I'm going to try to do this one step by step. Switch R2 and R3. Okay. And then we could do what, half of row 1? Right? And then 1/3 of row 1 plus row 2, row 3. Oh, we don't want 1/3, we want 3. Excuse me. Okay. So the inverse of A Oh. And now we have an algorithm for determining the inverse of any matrix. Great. Terrific. All right. So just to recap what we talked about today, looked at the transpose of a matrix. We looked at what the inverse of a matrix was. We reviewed finding the inverse of a 2x2 matrix. We looked at why we might want to find the inverse of a matrix, and it's to make solving matrix equations a little bit easier, or just a different way to solve matrix equations. So we've done 2.2, finished 2.1. We're going to look at 2.3. And this one is a bit more conceptual, and a little bit more sort of me just talking and showing some pictures. Let's see, 2.3 is really just about some characteristics of the inverse matrix, okay? So I will have you refer to page 129. Okay. Okay. Page 129 gives a list of, it's called the invertible matrix theorem, and it's really just a list of A, B, C, D, all the way up to L, sort of properties of an invertible matrix, right? So for instance, A is a square n by n matrix. Then the following statements are equivalent. That is, if any one of them is true, then they're all true. If any one of them is false, then they're all false. So, let's see. Let me turn this around this way. A is an invertible matrix. Great. So that means that if we have some matrix, and if A is an invertible matrix, then the rest of these things follow. A is row equivalent to the n by n matrix identity. We just showed that. That was our algorithm for determining the matrix, the identity. A has n pivot positions, right? If it's invertible, then it should have as many pivot positions as it has rows. The equation AX equals 0 has only the trivial solution, right? Well, if it has n pivot positions, then it has to be a matrix that could make a homogeneous solution, or have a homogeneous solution have the only solution be the non-trivial, the trivial solution, excuse me. The columns of A form a linearly independent set. That sort of ties in with when we're talking about homogeneous equations, right? If matrix A, like AX equals 0, if that only has the trivial solution, then it has to be the case that the columns of A are linearly independent. And the columns of A, oops, read that one. The linear transformation X going to AX is 1-to-1. So that's something that we haven't really talked about. That one's important. So that says that if matrix A is invertible, then the transformation T that multiplication by A represents is 1-to-1. Okay, so there's another way of finding out whether or not a transformation is 1-to-1. It's 1-to-1 if the standard matrix A for the transformation T is invertible. Okay. The equation AX equals B has at least one solution for each B in Rn. That's the definition of 1-to-1. The columns of A span Rn. The linear transformation X to AX maps Rn onto N, or Rn onto Rn. So great, if we can determine whether or not A is invertible, then we now know not only is it 1-to-1, but it is also onto. Okay. There is an n by n matrix C such that C times A equals I. Okay. And that would mean that C is the identity or the inverse. There is an n by n matrix D such that A times D equals I. Right? There is an n by n matrix, and A transpose is an invertible matrix. So obviously if A is invertible, then transpose of A should be invertible. All right, so become familiar with that theorem and those properties. Okay, that's going to be that's going to come up on tests. Those would be great true or false questions. Hint, hint. All right. So characteristics of inverses. Them. Talked about page 129. I'll have you look at that on your own. Okay, inverse transformations. Let's see. here's a place, and here's an element of that place. And here's matrix A, and it's going to take me to AX. Okay. If I was here and wanted to get back, I would use, you guessed it, the inverse of A. Right. Sorry. Okay. So this is a graphic, or not really a graphical, but an illustration of what it means to have an invertible function, right? Okay, so let's see. Let T be the transformation from Rn to Rn. Okay. Be a linear transformation and let A be the standard matrix for T. Okay. Then T is invertible if and only if A is invertible. Okay. And then let's try to dull that down and make that be a little more nice. So S of X will equal the inverse of AX. Okay, this is my inverse transformation. Not inverse A, it's just inverse AX. And you should know from, at least from calculus, that if I compose the inverse with the original function, I should get X, right? Okay. And that works in the other way as well, right? Okay. All right, so if I have some transformation that maps Rn to Rn, and it's a linear transformation, A is my standard matrix for T, then T is invertible if and only if A is invertible, so that my inverse transformation S of X is the inverse of AX, and the composition of the inverse transformation with the transformation is X, and conversely, the composition of the transformation T with the inverse transformation S is also X. And this is true for all X in Rn, right? And that's really it for 2.3, okay? Inverse transformations, okay? So problems that you might see that involve this idea is I might give you a transformation and ask for its inverse, or I might give you a transformation and then give you a place in the codomain or the range and ask for you to tell me what took me there. And a good way of doing that would be finding the inverse and going back to where you started instead of solving the equation AX equals B. You could just multiply B by the inverse to get what X was, right? Okay. I would love to keep going on and talk about partition matrices, especially since it's really just vocabulary, but I get the feeling that this has been a lot. So let's call it a day, and we'll pound through partition matrices come Wednesday. Now, I don't believe you have a quiz this week. Damn, I had an assignment sheet made up, and I was going to print it out and give it to you guys today. Let me pull that up. Actually, it's really easy to pull up because I'm on my phone computer. Mitchell Van Doom says, "Nee." Interesting. Oh, Van Dorn, excuse me. All right, so let's see. I guess I could just post this to Blackboard, but for the few of you that are here, let's see. I've got a quiz scheduled for this Friday. Covering 2.1 through 2.4. Okay. So we will finish 2.4 on Wednesday, and then it would be optimal for us to be able to get through 2.5 and 2.7 as well. All right. And then after the quiz on Friday, we'll start with the new chapter 3. There is no unit test for chapter 2. Chapter 2 and chapter 3 are combined into one unit test. That will be 2 weeks from now. Exactly 2 weeks from now, actually. All right, so that is it for today. I hope everybody enjoyed. I'll have this posted on Blackboard as soon as I can. And have a good rest of your snow day or ice day or whatever it is.